Okay, so here we continue with the practice exam. We're at number 28. In which of the following does hydrogen have an oxidation number of positive 1, more than one possible answer? So hydrogen here is in its elemental form, so it's 0. Hydrogen here would be positive 1, with oxygen being negative 2. Here, potassium would be positive 1 and hydrogen would be negative 1. It's one of the weird times when hydrogen is negative 1. It can only be negative 1 when it's with a strong metal cation. And then HCl, hydrogen would be positive 1 and then chlorine would be negative 1. And in this case, in CH2O, the oxygen would be negative 2. A good guess is that carbon would be positive 4, so that means hydrogen would be negative 1 each right here. So the good guess comes from looking at carbon right here being in group 4. So in which one would the oxidation number be positive 1? Looks like positive 1, and positive 1 right there. Oh, here, I'm sorry, here it's negative 1. So those two would be positive 1 in that. The other possibility is that carbon right here would be negative 2. Oh yeah, let's not go that down that road right now. Let's keep it like that. Let's see. What is the oxidation number of sulfur in this? So hydrogen right here is positive 1. There's 2 of those. Sulfur would be something, and oxygen's negative 2, and there's 4 of those. So we have negative 8 and positive 2, so that's negative 6. So that means this would have to be positive 6 right here. Which elements are reduced and which are oxidized in the reaction? So here, oxygen's negative 2, because it's almost always negative 2. That means iron's positive 2. Negative 2 here, positive 2 for carbon. Here, iron would go to 0, and then over here, oxygen's negative 2, which means carbon's positive 4. So our change went from iron from 0 to 2, so that was reduced. And our carbon went from positive 2 to positive 4, so carbon went up, so that's oxidized. Number 31, which ions are spectator ions in the following reaction? All chloride ionic compounds are soluble except for silver, mercury, and lead. So to figure this out, we should write a net ionic equation here to find out which ones spectate and don't do anything. Titanium solid just remains itself. The acid, hydrochloric acid, would split up into ions because that's a strong acid. The chloride ion over here makes it soluble, so here it would be positive 2, and then it'd have 2 Cl minuses, and then it'd have H2 gas right here that would dissolve, but notice how it's different than the H plus right here. Notice how the titaniums are different on one side or the other. Here it's positive 2, it's in solution, here it's a solid. So my only two things that would spectate are the Cl minuses, so the Cl minus would be my spectator ions. Number 32, which ions are spectator ions in the following reaction? So for this one, write the net ionic equation again, so you'd end up with Ca plus 2 and 2 Cl minuses, 2 Na pluses, and a CO3 minus. Both are soluble because this one's got chlorides in it, and you know that all chlorides are soluble. This one's soluble because it's got sodium in it, so Na pluses are soluble. And this makes CaCO3, and then that's a solid, so leave that together. And then NaCl over here is soluble because it's got Na in it, and it's got Cl minus in it. So then the spectator ions would be the chlorides right here, and the sodiums right here. Both of those would completely dissolve and just spectate or watch. These right here would form a precipitate, and so those are the non-spectator ions. Those are the ones that participate in the reaction. Number 33, the balanced net ionic equation for the reaction is, and so it wants the net ionic for this, K2CO3, and then we're with MgNO3 and notice they're aqueous solutions, so these are both soluble already. Swap the cations, we'd end up with KNO3 on the right hand side. and then we'd end up with magnesium and the carbonate over here. Notice how I put the cation first in each one of those. Now let's balance the reaction. So I need a 2 here. That gives me 2 NO3s, 2 NO3s, 2 Ks. I got 1 magnesium, 1 carbonate, 1 carbonate. Okay? Next, we have to split them up based on their solubilities and whether they're strong electrolytes or not. And this one does form 2K plus and a CO3 2 minus, because K plus is soluble, it's one of these, and it's a metal and a non-metal, so it's definitely soluble, a strong electrolyte. Mg plus 2 splits up with the 2 NO3 minuses, because obviously it's soluble, it tells you it's an aqueous solution, and then it forms ions because it's a metal and 2 non-metals, so it would be an ionic compound. Over here, KNO3, that would split up into 2K plus and 2 NO3 minuses, because those are soluble. K plus is always soluble, nitrates are always soluble, so that's doubly soluble. And then the magnesium carbonate would be insoluble, because all carbonates are insoluble, except for ones from group A, or group 1, and this is not a group 1 metal right here, magnesium's in group 2. So the net ionic then would involve the magnesium plus 2, and it would involve the carbonate, CO3 2 minus, and then we'd end up with the magnesium carbonate over here on the right-hand side. There's our net ionic equation. All right, the next page has us solving some mathematics problems. These are ones that are using solution stoichiometry, dilution, or molarity. And so we'll start with some titration ones that are like solution stoichiometry problems. So in number 34, we're given a certain amount of these two items, hydrogen iodide, and so using the molarity triangle to solve for moles, it would be the molarity, 0.5, times the liters. Remember, 3 to the left, 1, 2, 3, so 0.030 liters. That would give me my moles of HI. With KOH solution, HI reacts in a 1-to-1 ratio. So since it's 1-to-1, for every 1 HI, there's 1 KOH. Once I know my moles of KOH right here, then I would take and use the molarity triangle right here to find the number of liters. And to find the number of liters, it's moles divided by molarity, so I would take these moles and divide it by 2 molar. So it follows the similar steps to stoichiometry, where we have the balanced chemical equation, convert to moles right here using the molarity triangle. It's not a limiter, so we can just go to step 3 and use the mole-to-mole ratio from the balanced chemical equation. And then step 4, convert to the asked for units. So we would do moles divided by molarity. And this turns out to be, I believe, 7.5 milliliters, I believe, is what the answer ends up being. Number 35. Titration problem now between HCl and LiOH. Swap the cations, you end up with HOH and then LiCl. After step 2, convert to moles. So now I need to take my molarity and multiply it by my liters. So the molarity is 0.4 molar. Multiply that by my liters, which are 1, 2, 3 to the left, so 0.020 liters. This would give me my moles of HCl. Put a multiply sign, put a line, put HCl in a position where it's going to cancel. And then I want to know how much LiOH is going to be produced, so put that as my new set of units. It's a 1-to-1 ratio. This will give me my moles of LiOH that are needed. It wants to know volume, so I would take moles and divide it by the molarity, so this number would be divided by 1 molar. And I believe when this one's done, it ends up being 8 milliliters for the answer. It'll give you the answer in liters, but make sure you convert it to milliliters. 36. This titration has HBr with NaOH. Swap the cations, you end up with HOH, and then with NaBr. Then we'll take our molarity triangle and we'll multiply the 0.2 molar times our liters, 3 to the left, 1, 2, 3, so 0.050 liters of the HBr. Then we'll multiply by a ratio to get rid of the HBr, and then make our NaOH our new set of units, which is a 1-to-1 ratio from the balanced chemical equation. This will give us our moles of NaOH, and if we take moles and we divide it by the molarity, we'll have the liters. So it's 2 molar that we'll divide it by, and I believe when you divide these, you end up with 5 milliliters of the answer. Come back with more in the next video.